Okay, for people joining this live stream, this is a design review for Wolfram Language version 12.2, which is coming soon, I hope. And this is about optimization, optimization in the sense of mathematical optimization, not in the sense of code optimization. And I guess we have a bunch of new features here. Can you introduce this?
Yeah. So we've in 12.0 and 12.1, we've been developing
Whoops, Roger, you
a
fuzzed out.
framework for convex optimization. So these convex optimizations are
You fuzzed out
convex
from
okay. Convex optimizations is fast both in theory and in practice, and it's global. So it's a basis for many of the future optimization we'll do overall. So this time around, we have extensions to that. So the first part here says that we can do those optimization over complex variables. In 12.1, we did integer variables, which is
Wait a minute, we've done real variables.
Real variables is the default, so it's always there. Then we extended to what's called combinatorial or integer variables.
Yep.
In 12.1. Now that's a different kind of difficulty.
So what functions does this flow into? I mean, this flows into maximize, minimize. Does it flow into, I mean, is it relevant for like neural net training and things like that? Or is it not relevant for that? Or does nobody know? Or what's the story?
So, well, I mean, this currently flows into all the convex related optimization.
No, I understand that. I'm asking about things outside of the optimization bundle in the system. I'm asking about completely different functions and image processing or something else. I mean, where does this get used?
Oh, optimization gets used, you mean?
Yes. These functions.
Okay. Yes. So they get used, heavily in statistics. Anything
so
with
we're
probability.
using our latest stuff. When we do a fit of a curve, we're using our latest optimization functions. Is that correct?
We actually do. So one of the things that we did in 12.0, and Rob can speak to that better, is that we upgraded all these fitting functions. Not the statistical model fit function, because that's another.
But so find fit, for example, is using fancy modern convex optimization. Is that true?
When it can. But we also have, I mean, one of the things we added to fit in 12.0 was fit with regularization.
What does that mean?
So the classic fit is basically least squares of AX.
Right. And why isn't that
B.
a convex optimization problem?
It is, but it's actually, but you can solve it simpler as a linear algebra problem. So that's, but if you add, for example, if you add a norm of X 1, so the one norm of X to that, what you do is you actually get a sparse set of the basis that best does the fit, and that is a convex optimization problem.
But so wait a minute. So let's say we were fitting numbers with errors. Is that still linear algebra, or does that require something fancier?
Yes, if you want to
mean by that.
Well, I mean, you have a weighting based on the error bounds.
Right? If it's just a weighting, then it's still the same problem.
No, okay. But so you're saying an L1 norm rather than an L2 norm?
Well, no.
You misunderstand. Well, let's go to the page. Okay, if we're going to talk about that. So the thing is that when you fit these coefficients and stuff, the question is, do you want to let these coefficients get arbitrarily big, or do you want to penalize lots of big coefficients? If you penalize the big coefficients, it's called regularized fitting, and they have a bunch of fancy names like lasso and so on. Okay, so people often know them by those kind of names. So if you go to fit, for instance,
what's also called, I mean, it's called basis pursuit or ridge regression.
Yeah, okay. Depending on how you penalize them, they have different names.
Fit regularization. Oops. Where are its examples?
That's missing.
Why are they missing?
I don't know why.
Oh, you mean a build problem?
Fell through the cracks, or it's a build problem.
Okay, so people might know them by these names instead.
No, that's
okay?
fine. I mean, this looks
Lasso
good.
and so
It's a
on.
pity that the examples fell off. That looks good. So is this also supported in find fit for nonlinear fitting?
Yes. Well. So if you give find fit a linear model, it'll automatically use these, and you can.
But what if we give it a nonlinear model? Are there nonlinear models for
yes,
which?
you can also use the fit regularization, but it's not necessarily going to be a convex problem. So it may, we don't necessarily have a global solution, but we do support the regularization.
So question here. Yeah, so there was a goof up with fit regularization. It's even wrong on the web. Okay, so there's a question here. All right, so basically we're using the fanciest optimization methods we can when we can use them in this case.
Yeah. Let's ask, that your original question, where is it used in our system? So it's gradually making its way into more and more parts of the system.
Okay.
So there's one thing that we looked at yesterday, for instance, these minimum volume ellipsoid bounding regions.
Yep.
That's using our best optimization. Okay. There's a bunch of graph operations that we have added, and there are a bunch on the to-do list that will also be just basically optimization problems.
What about graph layout?
Graph layout is an optimization problem, but it's as a dedicated solver. So this is the other thing that happens when you have, if you can, so what we develop are general purpose optimization as opposed to
I understand that. I understand. So
purposes.
you're saying spring electrical embedding could work this way, but we shouldn't have it do that because we have a completely optimized piece of code for that particular case.
Exactly.
Fine.
But it was written by our previous, optimization team that knew exactly what needs to be optimized to get it to that level of performance. See what I'm saying?
Right.
For that problem.
But okay, so you've done a scan of the rest of the system, like image processing or something, like, I don't know what, like image
we're flowing this in gradually, partly by us doing sometimes prototypes. We've done a bunch of prototypes in this team, partly getting, in the teams to be trained up to see what's available, and they see it. And so then it's a question of when it sort of fits with the, it's some mix of this opportunity is big enough, we should do it now because it's easy, it's available, versus let's do it when we come to that point and we know that we can now utilize this.
What about things like labeling on plots and labeling of?
So labeling, that's also an optimization problem, but it's not using convex optimization. It's because some of the things that you need to test there, I mean, it's not convex to begin with.
Okay, all right, fine. So okay,
but our system is full of optimization problems, and many more will be there in the future.
All right. I'm just checking that you're going through and making sure that all this stuff flows in correctly.
Yes.
Okay.
And there are many things on its way.
Let me make a trivial, silly comment for maybe Avery can note this down. There are these black lines between these rows. I don't think they've been there before. Screen capture, ask design. They look wrong to me. Something went wrong here. Okay. Somebody, can you do that, please? Should I do it?
Yeah, I just screenshot it.
Okay. All right. Fine. Okay. Optimization solver extension API.
So here's the idea.
I think I understand the idea. You can plug these in as the core optimization thing. And once we've processed the problem to the point where it can be fed to these things.
Right.
Right.
And anybody, the idea is that anybody, including companies, should be able to write these.
Yeah, I understand.
So if you're an academic,
I got it. I got the idea. Right. So the question is, do these things have file formats, or what is the?
I mean, they do have file formats, but we don't want to communicate with them in that way because it's very.
Okay. So what is the API? Where's the documentation for the API? You said documentation.
Yeah, there is there, but it's done as a packlet, so I don't think it's accessible
you want to show it to me on the screen?
Yeah, Rob can share it.
Okay, go ahead.
Let me pull it up. So.
I mean, I assume that's why you put it on this agenda.
Yes.
Okay.
Yeah, this is not totally refined yet, but
okay, ready to share? Yep, sharing.
Yeah, am I sharing? Okay.
No, go ahead and share.
Oh, okay, it didn't work. Okay.
Go ahead and share.
Okay, that should work now. It'll take me a little while to get there. Oh dear me.
Okay, you know what? Let's go on. And
yeah.
You can come. Are you ready for it or not?
No, let me get it. Go on, and I'll get it ready. Okay, so let me unshare, and then when I want to have it ready, I can let you see it.
Okay. All right. Okay, what's next in this agenda?
Okay, so then there are two, so the other thing that we've extended for these to work on complex numbers, complex vectors.
Okay, you said that.
Okay.
What's
so next up,
okay.
Hold on.
Okay.
The next big thing is that we're dealing with parameters. So you do an optimization problem and you have parameters where those parameters can attain some range of values. They live in a set, basically. Okay. So the two things we have here is robust and parametric optimization, and there's a third coming called stochastic optimization. So the easiest to explain first, I think, is actually parametric. So maybe we should go there first. So the idea is this: this is set up to be able to solve optimization problems.
What is parametric function?
This is the thing that we created for parametric ND-solve, and it returns a function that takes parameter values, and given those parameter values, it goes ahead and solves and gives you the actual solution, which is typically.
I bet there are other places we should be using this. Has the machine learning group been aware of this function?
It's been there forever, so
I know it's been there forever, but I don't think they're aware of it.
Probably not. I would guess.
They're probably not.
I mean, we really should be thinking about where else this can be used. Yeah, I remember this now.
Yeah. So our design, I mean, it's quite separately from this, so we have tentative designs for parametric functions for most of our numeric solvers. This is now for optimization.
So the idea is there is a parametric family. There's a family of things that say parametric blah, 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 that return a parametric function, which when given the parameter values,
gives you the actual solution for those. Because then it's a fully numeric thing. But it does a second thing, which is actually crucial, because you can now compute so that first thing of repeated solving efficiently, people were using that, for instance, during COVID now to fit differential equations.
Yeah, right.
Okay. So it's super useful for that.
Well, I mean, that's that's the idea of using machine learning for differential equation solutions, for example.
No.
Yes.
No, this is parameters in differential equations, and now you can adapt them and fit them.
But actually, I think Stephen is right. And not only, I mean, part of the stuff I did with sensitivity for optimization is from a paper about using optimization in machine learning. And one of the things these parametric functions allow us to do is provide the correct derivatives. And I have a design for that we'll want to talk about probably later in the machine learning meeting that allows you to get the derivatives needed for the back propagation process.
Okay, so there's two different ways around here. One thing is using these parametric functions to provide the thing that is going to be fed to, to represent the automatic differentiation, so to speak.
Yes.
Another different thing that I was saying is that the workflow of approximating the solutions to a differential equation by neural nets, as opposed to approximating them by these parametric functions, is something that should be uniform in this workflow. That is, it should just be a method choice, whether you're going to use one of these parametric functions.
I don't think it's the same. I think you're both confused.
That's different. That's different.
I think you're both confused.
Okay.
So the idea of using neural nets to approximate differential equations, that will need obviously an actual function representation when it comes out. But it's not parametric. There's nothing parametric about it.
Why?
Internally,
that's the whole point. That's the whole point, is to make something where it's not just a particular neural net solution. It's not just a particular differential equation solution, but a whole family of differential equation solutions where you don't have to solve each individual one, but you're just using the neural net to interpolate.
Okay. So in that sense, it is similar.
Yeah.
Or a related idea.
Well, but in particular, predict, for example, predict returns a predictor function, right? Which to me sounds very similar to the parametric function. Now, maybe it's different in the sense that the predictor function typically is being fed large lumps of data and predicting, the score, the chance that the spacecraft blows up or whatever it is, right?
Mm-hmm.
But whereas here you're feeding in a small number.
This parametric function is different in the sense that this one understands the underlying problem. What it does a partial compile effectively.
No, I realize.
When you then feed it parameters, it's much faster to get to the solution.
I get it. I'm saying I don't think they're actually different things. I think that what's happening is, again, you could imagine a parametric function that emits a predictor function that is parameterized by parameters that then can be applied to data, right? So it's a two-step thing. The parametric function emits a function. The function is then applied to actual values or data, right?
Possibly.
Yeah, I think so.
I think the predictor function is largely even if I'm in there, I don't really know what's in it. I think it's a goggle. It's sort of, a mix of a bag of methods used for predict.
Exactly. That is correct. But what I'm saying is, you could imagine a setup where there is a parametric, where a predictor function, where its output is a predictor function, right? As opposed to its output being a number, like 7 or something.
Yeah,
sure.
Right?
Absolutely.
So, and to me, this is a mechanism for something that we have not had, right? But which I think we've had interest in, which is neural nets that emit neural nets, so to speak.
I see. Well, in that case, we are talking about this conceptually the same.
I think so. And I think that's what happens in, I don't know, it's not quite the same as reinforcement learning again, but these are all related concepts. Anyway, talk to Etienne and those guys about this. I think there's some unification here that can be done.
So the other thing that you can do here, which is quite important, is to compute the sensitivity. Like, say you have an optimal solution.
Yeah, I get it.
How sensitive is it with respect to changes in some underlying assumption?
So what's the default for this primal minimum value? Why is the first example not the default example?
The default we chose to be consistent with the other convex optimization function, which is to provide rules for the results. So if you want to plot it, you do that. Versus the next example shows the default output in terms of the rules.
So the interesting here is to see how the optimal value depends on the two parameters. Whereas the default is to get the actual location of the optimal variable values as opposed to the optimal objective value.
Say that again. What?
It gets you the variables. X and Y are the variables in the second example there.
Yes.
Okay. But the objective is abs x plus 2y minus 3. The value of that objective for the different parameters is effectively what we plotted in the example above.
But it's basically like n arg min versus n min value.
Yeah,
I understand, but what we've done for minimize to give the value and then give a list of rules for the position?
But you don't want that. For easy processing, you don't want a composite output like that.
If it was an association, you'd be a happy person.
No, you still have to then deal with it and take things out. But
I don't understand. You have to specify what you want somehow, right?
Yes, yes.
And so many of our functions, if you don't tell them anything, they'll just give you an association, but they have an additional argument, which is a property argument, which then either is an auto extractor into the association. That's what conceptually you can think of it as,
Sure.
or it shortcuts the actual computation. So
Yeah.
why is that not how these work?
Because I don't think you want that whole association most of the time.
I agree. So the only question is, look, the question is, in this case, it seems
and
like
also I don't know what the cost is if you were to, I mean, they usually have a lot of properties. That's a long list.
Fine. But so what you're saying is normally you want a particular property, right?
Yes.
Okay.
Or a set of properties. Yeah.
Well, that's fine. But then the default case is I'm just objecting to the fact that the default case gives you a property incompatible with what minimize gives you. Since the default case, my guess is, will not be used very often. The more common case will be something where you're specifying, I want the primal this, that, and the other.
I would disagree with that. I think we chose the default case to be the rules because that's the case that's very commonly used, because people typically want to, if they want to post-process the result, they want to know where and if they want to find out what the minimum value was, they just take the objective and do / the rules, which they get out, which is the default. So it's really convenient. Whereas with and minimize, you have to do, part of result 2.
I know.
To do so, this allows you to do the replacement.
The question is, why is this compatible with n minimize? It's not.
It isn't. We all of these convex optimization functions, they have this return value as opposed to that composite return value.
Fine.
And they can report so many more things that we can't ever do for general optimization.
And it's quite easy to mimic the n-minimize return value by just a list of those two of those properties.
I agree. I understand.
Yeah.
All right. I mean, I don't know this field well, so I don't really know. I mean, things like
this thing,
whatever. I don't know this stuff.
Well, this is what we introduced for sort of our convex optimization, that we can have matrix variables and vector variables and so on, which is which makes the formulations very compact and almost, I would say that they're close to impossible without that. And use cases for this. Why would you want this kind of function? So here's a couple. Let's say that you want to, since we talking about games the other day.
Yep.
Let's say that you want to maximize the minimum. Okay. So you have some variables that we call parameters here, but you want to maximize outside of that minimization. You can now do that.
Okay.
Do you know what I'm saying?
You
can have these nested type of or hierarchical optimization problems.
Yeah, it's cool.
Okay. Another case, which is basically more or less similar, which is like when you do vector optimization, meaning or multi-objective optimization. Then what you typically want to compute is the Pareto surface of optimal solutions.
Yep.
So you don't just get one solution, you get a whole surface. That means you solve a shitload of optimization problems, and they're usually called scalarization methods. They map it to what our optimization methods are, a scalar optimization methods.
Yep.
But you're going to solve a lot of them.
Okay.
Stochastic and robust are similarly where you deal with parameters in other ways, where they're equivalent to solving many, many optimization problems. So I can talk about those too. But do you understand robust roughly?
Yeah.
I think that there's a good application example. We haven't really filled that out that much yet, but I think that there's a few. Okay, robust. Let me explain what that is then. So robust, if you have these parameters, what is the safe optimization value that you should use? So let's say that I want to, I want to minimize something, but there's some uncertainty in my parameter values. And the way I express uncertainty here is deterministic uncertainty. By that, I mean the parameters live in a set. Under those.
By the way, are you sure you want to use this thing for in a to represent function? I think you should say function here.
You think we should? Fine, I can change that to function.
I really would. I mean, I'm a big fan of introducing this more seriously in the language, but I don't think people know it enough yet.
Yeah, fair enough.
And I think
I think it's quite expressive, but yes.
I think it's great, and that's why I want to make vertical bar dash greater than produce it, so people will use it routinely.
So,
go ahead.
But the mission, okay, so you're going to minimize something, and you have this uncertainty, meaning the parameters live in a set. Now, what's the worst case minimum that you can get? You know, it's basically like maximizing with respect to the parameters, effectively. Or you could say that you want the minimum that can be valid for all possible values of those parameters.
Yeah, I get it.
So you have
how do you weight? I mean, I don't understand. In the for all thing, it's like it's most important for it to be good for these values of parameters.
No, you don't do that. You just say for all. So it has to be possible. It has to be valid for all possible parameter values. The problem with that for all is that you can't eliminate it. So it becomes what's called an infinite optimization problem. So you have basically an infinite number of conditions.
Yeah, I get it. Right, I get it. So can we write that with a for all here?
We can't right now. We've just made that possible in the symbolic case. So
in other words, there's an optimization. We
should probably actually, Rob, I didn't think of that here, but we should probably parse and accept for all, maybe.
Why not? But I mean, so you're saying that in minimize, I can have a for all in it.
You can soon.
Okay, that's exciting.
It was, yes.
Yeah, but I mean, I think the for all kind of makes sense, but we'd have to include the parametric constraints within the for all then, right?
Exactly. Yeah, it just needs to be parsed out in the right place, but we could do it, and it would be kind of a a consistent.
That would make it clear, wouldn't it?
Yes, it would make it clear, because that's exactly what it means.
Where is the for all in this statement otherwise?
The either state there would be a for all that 10x where you see the x variables. There would be a for all in front of that, and then these parameters beta and alpha would. There's an and. You know, that list represents an and first of all.
Yep.
Okay, so there's an and of those two conditions on x and y. There's a for all in front of those. And then those two conditions on the parameters, alpha, beta, would be the for all condition. So it's the second argument of for all. You know, it's a three argument.
Yeah, right. What? I mean,
for all takes three arguments.
Alpha, beta.
Sorry?
I mean, it will be for all alpha, beta.
Yes.
And then you put those last two that only have alphas and betas in them.
Okay.
You would take
Not
it.
quite understanding that, but I believe you that I don't think we need to go. I mean, the only thing I'm confused about is usually for all has a payload.
Yeah, but then the payload is the last payload is those x and y inequalities, the and of those two. That's the actual ultimate payload.
I see. So it's a predicate. It's saying for all alpha and beta, these inequalities are supposed to be valid.
No, almost. You have to. They're in two different. One is conditions on the quantified variables, and the conditions on quantified variables gets put.
But this is a list of both. These are the quantified variables at the end, right?
Yes. Yes.
And so this list mixes non-quantified variables with quantified variables.
Exactly. So the x and y are free within the for all.
I get it.
Yeah. Yes. Yeah, that's the issue.
Well, I mean, the syntax you have right now seems to me perfectly sensible for that. Whether there's a for all syntax that's clear, I don't know.
It's also identical to the parametric optimization, and it will be more or less identical to the stochastic optimization. So the only difference.
Stochastic case will say alpha and beta are picked from some stochastic distribution. Is that correct?
Exactly. Yes. Yes.
So normally here, you could say X element of blah blah blah. Here, is that correct?
Yes, you can do that.
Actually,
in that argument, as opposed to in this argument.
Yes.
Which argument do you put that in? Or do you put it in this constraint?
You can put it in if that element depends on the parameters, I think you have to put it in that constraint set. But if it's, it's say X
okay, fine.
element,
I think it's a fine place for it.
It can go either place.
Okay. Okay. So in other words, you could also say alpha is distributed like a normal distribution with blah, 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 and that could go in the constraint argument there.
That's
yes.
Right. Okay, cool. All right. A question on our live stream about whether various people saying this looks like very, well, Seth saying it looks extremely useful, good. Somebody else saying it looks nice but too mathy. Look, this stuff is complicated stuff, right? This is when you need it, you really need it. And that's what it's for. If you've, it will be used implicitly in a lot of places. That was what we were talking about a little bit earlier, where you might not have known that under the hood it's using fancy convex optimization and so on.
So the other thing that's happening in the world generally, so when we could just barely compute things, that you couldn't really deal with parameters or uncertainty.
Yeah.
Now progressively, we want to deal with uncertainty in more and more, so we can assess reliability and robustness of our computation.
I understand. So when you can do a whole family of computations, you can assess robustness and so on.
Yes. So
right.
That's starting to happen, and this is going to take some time to flow into all of our solvers, but that's progressively what's happening.
Good. So okay, let's. There was a question here about, is it useful for hyperparameter optimization in neural networks? Do you know?
No, I don't know, but there is,
I mean, hyperparameters are usually sort of distributionally modeled, so that's kind of falls into the stochastic realm.
Something to ask Etienne.
Yeah, these are things when you want to have kind of what's the safe return on that portfolio given certain uncertainty in.
Right. That's right. Right.
Or you're going to make an actual engineering design where there's certain variability in components, but you want to guarantee that it will function.
Right. So here's a question from Nick on our live stream, which I think is a good question, which is, are there going to be wrappers for specific kinds of problems like routing, scheduling, and so on?
Yes. We already have a bunch of them, but there's more coming, many more coming.
What's an example of a wrapper for like routing?
Well, there's a ton of them in graph computations, like the whole maximum flow. There's a lot of these.
Does MaxFlow use this stuff?
No, MaxFlow is MaxFlow is basically linear programming, but on specialized structures that can utilize those structures very directly.
Okay, but so in the family of things that, I mean, scheduling, routing, etc., that directly use convex optimization. I mean,
yeah.
What is the
one of the limitations, okay, in the setup for the MaxFlow problems and shortest path and all of those things, is that you can only there's slightly rigid the family of problems that you can formulate. If you want a richer problem description language, you need to go to optimization. So basic scheduling can be done with those flow problems in graphs. But if you want something more general, it becomes an optimization problem. And now you're in this business. Some of which are convex, some of which are non-convex.
Okay, but the question is the wrapper for, I've got a specific problem. I'm trying to do, a routing problem for, I don't know, microprocessor design or something, right? how do I formulate that problem in terms of, is that problem, I mean, this is like, we got whole things like system modeler to formulate things as differential equations. What is the analogous thing? I mean, these old systems, I don't know what was called, AMPL or something, these very old systems for doing mathematical programming, whatever they were.
Well, AMPL is actually for optimization, pure and simple.
Okay.
It's like our symbolic layer here.
Okay. Fine.
It's actually very good. It's not bad. It's very old, but it was done by Brian Kernighan and Richard Forer and these people. So it was pretty good.
But so what is the higher level description language relevant for these problems?
Yeah. So our okay. Often you have a domain description language that's more specialized to the domain in question.
Yeah, right.
So that it becomes easier to formulate these problems, both to express them and express them shorter. Now,
look, that's what after a decade, that's what we've done for PDEs. We're finally getting a nice description language that actually lets you compute fairly easily, a bunch of PDE situations. So I guess I'm asking what the analog of that in this is.
Well, but we've added many more description languages. We've added a description language for graphs. We've added one for probability and statistics. We've added.
No, I understand. But so I'm asking, what are the ones which are heavy lifting, problems that get solved with convex optimization? What are those kinds of domains? Like in robotics, there's a domain in robotics, isn't there, where you use this kind of stuff?
Yeah.
Is that true?
But it's significant to develop these domains, each one of them. So that's a pretty, because the minute you introduce, let's say, robotics, you don't want just that.
No, I'm aware. So I'm asking, what are those domains, and what is the map of what, each domain has a certain cost to introduce it and to get deep enough and general enough that it's usable. So I'm asking, what are those domains?
Well, they touch more or less every domain that we work on and many that we haven't worked on. So, control theory, signal processing, image processing, machine learning, statistics.
Those are all generic, right? Right. I'm asking for things where we don't have a dog yet in that fight. So I'm saying, I mean, something like machine learning, we obviously have tons of stuff already there. I'm asking, are there areas we don't have stuff in? That, because machine learning, we can do a bunch of stuff right now. Is this useful for hyperparameter optimization? We don't know, right?
I don't know. It seems like a strangely asked question to begin with.
No, it's not a strange question. Hyperparameter optimization is a thing. Is quite as popular now as it was maybe 2 or 3 years ago. But that was kind of the a peak issue for neural nets. Is it's sort of, how do you get the best network to train for some particular thing? It would be an obvious application of this if those optimization problems have the right structure to be convex optimization, which I have no idea.
I don't know either. It seems unlikely. I think
it's unlikely too, right? But I think it's a question to ask Etienne.
So that's the question of sort of what rate have these domains been formulated as optimization, and then secondly recognized as convex optimization.
I understand.
Okay. So in economics, in finance, that's progressed pretty far. In control theory and signal processing, that's progressed very far. In some of these routing problems that you talk about, like circuit routing, I mean, we do routing for graph layout, but it's very simplistic routing. Yep. But we have a bunch of application examples that are effectively layout and routing problems.
Right, but the question is, when do we get the wrappers that allow people to easily be able to formulate routing problems using these things, where you don't have to?
We don't have them. I don't have a plan for. I have a big list. And there's a question of what rate that we can sort of portion them out.
So most likely, those things should not initially be built. I mean, like for example, I remember we had an example that was in the 12.1 blog post and things like that. There was an example of using convex optimization to pick, to figure out how to pack certain rectangles, right?
Sure.
It was
that thing was unbelievably painful to program. Remember how painful that was to program?
Yeah, it took some effort.
Right. So my question is, what is the family of problems that are like that? And is there a domain-specific way of describing those that's useful?
But do you think of that as a new domain or an existing domain?
That's a new domain. It's a new domain.
Yeah.
It's really a new domain. It's not, it's not machine learning. It's not image processing. It's something different. It's something where we, that one might reasonably say, it's some planning optimization type thing that isn't something we're currently doing.
Okay.
Right. So, okay.
Yeah,
look,
I mean, as I said, it's all over the place in chemistry. It's at the rate that
I understand. I understand. So there are two questions here. Question one, we've got existing functionality. Can we use these algorithms in that existing functionality? That's question one, which it sounded like you've done some work on, but it's not clear that that's gone all the way.
No, it's not gone all the way.
Fine. Second question is, are there new, preferably horizontal areas that can be attacked? And for example, that floor area optimization thing, I don't know what the general class of problems like that is, and whether there is a simple to describe class of problems, or whether, to give one example, like in the setup of differential equations, by the time you have to have a whole system modeler system to set up the differential equations, that's not a simple to deal with domain. Right?
That's right.
Even the PDE domain, it's clearly fairly complex to define PDEs with all their boundary conditions, et cetera, et cetera, et cetera. So what I'm asking is, are there any areas in the area of various kinds of scheduling and all this kind of thing that are, like here's an example, and I don't know whether this is an optimization problem of this type or not. Okay, question that came up for random schools right now. They're asking the question, they say, okay, we're gonna break the classes in 4 groups, right? And people could, I'm not sure it's a good social idea, but let's imagine that everybody could pick who their top, friends, the top people who they'd like to be in the same group as them are. Do you understand what I'm saying?
Yeah.
Yeah. And then the question is, can you allocate groups to give people their most satisfying kind of thing? By the way, somebody doesn't have themselves on mute and are making all kinds of background noise. I think, but so is that an example of something which would be
possibly? So I still have a giant list of that, and initially I set out for 12.1 that we were to focus on applications. It was very hard for us to execute in the team. Okay.
No, I understand, but I'm asking, it could be the case, okay, that there are no kind of easy to access horizontal applications, right? It could be the case that every application area is a pretty tall vertical tower, right, that requires significant support, as systems engineering does, as PDE solving does, that to set up these problems, is complicated and requires lots of domain knowledge, right? I don't know. That's what I'm asking, right? And by the way, a couple of things on our live stream here. They're just some questions of interest, which I think I know the answer to. But Push is asking, is simulated annealing and so on used in these optimizations? I would think yes, somewhere, but these are much more powerful general techniques. Is that a fair?
Yeah. So yes. So one of the topics which we already have a function for and minimize uses some of these non-deterministic methods like simulated annealing. There will be updates to those functions too, both to add what's called deterministic methods that will guarantee globality, and these non-deterministic methods which will not guarantee globality, but it's sometimes the only choice you have.
Right. Guaranteeing globality just seems like one of those super difficult things.
Yeah. Convex is one that does it.
No, I understand.
We have aligned to now to many more domains that we can do it for.
Okay, but so look, in the history of these things, I think you've even explained this to me. I mean, back in the day, you approximate everything with linear stuff, and then you do linear programming. The point here is that now we can do convex optimization almost as efficiently as linear programming.
Yes.
And therefore, now there's the question of, well, now there is another kind of approximation that can be done, And,
Right.
you know, we can do that. Now, the question here.
And that's effectively part of what's happening. Some of it's happening in the different domains, as you call it. When people recognize this,
Yeah, I get it.
You can confidently say that your problem is solved.
Right, I understand. But so what you're saying is, you know, you might be able to solve airline scheduling, you know, which has been traditionally done with linear programming. Maybe there's with some extra twiddle of that, there's a version that can be done with convex optimization. I don't know.
Well, I mean, so first of all, linear programming is convex optimization.
I understand, but it's an example.
But the thing for airline scheduling might be you want to make it robust, for instance. You want to make it, and we've all seen what happens when it's not robust.
Right. Well, fair enough. Okay, I think there's a question here about Lagrange multipliers, which I assume are the way that you do a bunch of constraints, but I don't really know.
That's the dual problem. We don't describe one for robust convex optimization, but we do for, you know, parametric optimization and these other optimization functions.
So the dual problem is using the Lagrange multipliers as, I mean, the Lagrange multipliers allow you to put in a constraint on what you're optimizing. Is that right?
Well,
I'm confused.
The dual problem is basically giving you what the Lagrange multipliers are for the.
Oh, I see.
For the
do we mention
conditions.
Lagrange multipliers and when we describe the dual problem? Might be nice.
Not sure we do, and perhaps we should.
Yeah, sounds like a good idea. Now, various comments here about how confusion about why this isn't more related to machine learning. Because, you know, the claim is machine learning training is just optimization. Yes, it is, but it probably isn't this type of optimization. Is that a true statement, or is that not a true statement?
No, it's true. Machine learning is full of local minima.
Which is what you typically want. I mean, bashing through to a more global minimum is what you want, but finding the true global minimum is something you're very unlikely to achieve.
Yeah. But this might, you know, one of these things might be a layer in a machine learning thing.
Right. So that's what we need to, you know, that's what you guys need to talk to Etienne about.
Yep.
All right. Let's have a quick look here, and then I want to see your API thing, and then we go to wrap. Okay. Local optimization. All right. Vector optimization. What is adjoint? I know directional derivative. Why isn't that just grad? What is
directional derivative?
Go ahead.
Scalar. I mean, so, okay, so this is something Rob wanted to bring up. It's not fully cooked, but we wanted to hear your opinion about it. And this is something, so directional derivative, it's an elementary topic, comes up in the first calculus class. And that's like, if you point in this direction, what is the size of the derivative? So it's a scalar value, not a gradient. You can compute it.
Oh, I see.
So basically dotting with a gradient.
That. Yeah, okay,
yes,
fine. The projection of the gradient in that direction.
Exactly.
Okay.
Yes.
Yep.
And the thing I called adjoint derivative, I haven't figured out a good name for it, but it is effectively the gradient. So this is a sort of thing that machine learning uses for backpropagation.
But why isn't it just called grad?
Because we have a function grad that's symbolic that just computes it. We want something like it's like an operator form like derivative versus grad, which is a symbolic form.
You have to open the pages, but as I said, they're not fully cooked.
I did talk to some of the machine learning people about this, and they said the essential thing is that it doesn't try to evaluate things symbolically.
Right. So this is basically a thing. I see. So it's the analog of derivative. Why? Yeah. Okay, directional derivative. What is its second argument? I mean, directional derivative has to have an argument. Oh, I see. The directional derivative is going to have an order, and it's going to have a direction, probably.
No, it's going to. This design here came up with discussion with Jose, and he says so it has a direction instead of an order, so it's always a first order thing. Okay, so it has a direction instead of an order. Why isn't that
in the list? Why aren't those d sub i's?
Well, this came up with discussion with Jose.
Okay, so my suggestion would be that is in a list there, and that way it gives you the possibility of having additional arguments to that directional derivative thing. And I think the name directional derivative makes sense.
Yeah.
And but I mean, what you can do there is just like we say. So also, I don't understand how you would do this. Oh, I see. The issue is that those d sub I are going with the positional arguments x sub I in here, right?
Precisely.
Yes. Yeah.
Right. And so then, but if that was a vector valued function, I mean a vector eating function, then
yeah, so those d sub i's can be, each of those d sub i's can themselves be vectors.
Just like so if this thing is eating vectors here, then that will be a vector that expects to eat a vector here.
Yep. Right. So that the structure of the d's has to correspond exactly to the structure of the x sub I.
I wouldn't call them d though. I mean, really wouldn't call them d. That suggests dimension. I mean, it is. I don't know what you call them, but it's a you know, that is, it's a vector v or something.
Maybe I could call them v or something. Yes, v right. Might be better.
Okay, so adjoint means what again? So I understand the directional case.
The adjoint is in the sense that instead, so the directional derivative, you take the Jacobian and dot with the vector, and that gives you the derivative in that direction.
Yep.
Okay. The adjoint, you take the adjoint or the transpose of the Jacobian and dot with the, I called it delta here. I'm not sure quite what the name to call. I mean, in the reverse AD literature, they use a bar for the notation. But basically,
anyway, these are going in a decent direction. We should discuss these in more detail, but this doesn't look crazy.
Okay, good. I just wanted to hear you say that, Stephen.
Yeah, right. I think these actually look.
Well, we could talk about this more when we have. I think we have a machine learning meeting that I'm in next week or the week following.
Fine. Let me see the API documentation.
Okay.
Ready to share?
Yep. Okay. Share. Okay. So let's see. So this is. Should I make this bigger to see?
I mean, I can see it, but I think it'll be helpful to other people.
Yeah. Okay. So
125. Okay. Now I'll make it bigger on your screen.
Yeah. There we go.
Okay. So can you just show me a piece of output? Okay. Lovely. What does the API look like?
Okay. So the API looks like this. You do register optimization solver.
That's lovely. What do you actually send the creature?
Okay, you send it associations. So we have an example where we actually crudely use find minimum as a method. So this is what you set. So you say, we're going to call this method the find minimum method.
Okay, so it's going to be accessible from the method option. Is that correct?
That's right. So if you then do it. In fact, here's the example. You just use method goes to find minimum, and it uses this method.
Okay, so let's see the association that gets passed.
Okay, the association is you give it the function which it's supposed to call.
You know, the fact that you use the nice barred arrow thing for the function, and you use the word association for an association is not very consistent.
Well, yeah,
and especially since you use an association.
I've actually got. When I first wrote this, I was used to using association, but you notice I've started to use this notation. So I'm slowly converting to that.
Right.
But yes, that's easy enough to change. Okay, so basically you say, okay, what types of constraints does this method support? Okay. And how does it support
that's a capabilities list of some kind.
That's a capability, exactly, a capabilities list.
Where does it feed into the animal, so to speak? Where does it actually, how does it take the problem that you have provided?
Okay.
And you know,
so it gives an association. This problem data is an association. Okay. And it has a bunch of fields like objective vector when the objective
can
is
we
described.
See that? An example of that actual.
The actual problem data.
So, I mean, one of the questions that I would ask is, if you look at some of our, at external evaluate, okay? External evaluate with respect to many languages can just feed, can convert our data structures to the data structures of those languages. And coming soon is external function, which will do that for things like C++. Am I making sense?
Yeah.
And so, for example, if the thing is in a dynamic library, if that's how it works, then, some of these things, then you should be able to do a fairly direct, call like that. But I guess I'm going to ask the question, if you take one of those random, the Gurobis and Cplexes of this world and so on, what is their interface? What does it look like?
Their interface is typically, I mean, the interface we're using to do those is a library interface, and basically the interface works like this: is you set up a model, and then you add constraints to it. Okay, and then you solve.
Okay, I understand what you're saying, but I understand. But what we have is things like x squared plus 3x plus whatever, a symbolically specified.
Right. So this problem data. So basically, those model setups will take an objective in the form of a vector. Okay, and that's exactly what this is. And they'll also take constraint specifications in terms of what type of constraint it is, and that's what these I called cone specifications here. That's what the constraint specifications are. Is it a equality constraint?
So you've turned this thing into essentially arrays. I mean, you've turned it.
Yes, we
have it as a thing. So there's a big packet of arrays, and basically what these animals eat, their food, they're not herbivorous, they're arrayivorous.
Yes, and typically they eat sparse arrays.
Oh, sparse arrays. How do you specify a sparse array to them?
Well, we just have a sparse array, and then library link supports a sparse array interface.
But what does it feed? The animal is a C++ animal or something, right? How does the animal eat a sparse array? I mean, I understand how you'd eat an array. Well, even that is kind of complicated.
Well, typically, different ones have different interfaces for them. For example, MKL takes a compressed sparse row interface, which is very much like we have. But of course, I'm trying to get this changed to be consistent with libraries. Like we have an inconsistent thing, which we're waiting to get that in the development supply.
Okay, hold on.
Others take a position.
Okay. So hold on. What you're telling me is there are certain native sparse array formats, like an array. If you're passing an array to a C++ program, if it's a one-dimensional array, there's not a heck of a lot of choice about how it gets passed.
Precisely.
Right?
Yeah.
If it's a two-dimensional array, there's already some issues, but whatever. If you're passing a sparse array, it's significantly more complicated because there's probably 5 different ways you might pass it.
Well, there's typically only two different ways. One is the compressed sparse row or column, and the other is this index value notation.
But when you say that, okay, you're saying by saying index value, for example, that's a struct or something in the C++ code, presumably. I don't know. Is it something else? It's an array of structs, or what is it?
Well, what's most of these things take an array of row index, array of column index, and array of values.
Okay, it's just like Fortran. So
just like Fortran, yeah.
Okay. Good to see that things have been modernized over all these years. Okay,
and
so the thing is, it's arrayivorous. It eats arrays. You have to just feed it a sequence of arrays. And what I'm trying to understand is, in the end, we have glue code that, we've had since 1989 or something for doing installs of external programs, right? Where you have a C function. Now we are modernizing that stuff. That's a piece of work that is coming out of, I don't know, Christopher did some work on this a couple of years ago. Now it's being put into the tooling stuff he's doing for the compiler, etc. Are you aware of this stuff at all?
Yes, I've been involved with the meetings that Christopher's talking about, some of the tooling stuff for the compiler.
Okay, great.
And I think the compiler will actually provide a really good interface to various C programs.
That's what I'm imagining, because I think the overall architecture there, which Christopher's been pushing for a couple of years, is to be able to make external function work with C programs. Okay, so external function will work with an interpreted language like Python or something, but it also should work with C. And for that, it has to be able to define a data structure, a struct, an array of structs, whatever else, define and then essentially be able to automatically convert our expressions to that form.
Yes, right? And one of the things I want to do, I mean, we're waiting for the graph group to finish, is to fix the index thing with the sparse arrays. But one of the things I want to do is and we've basically got prototype code to start doing it, is put sparse array into the compiler. Then we can actually write all of our sparse code with the compiler and interface to libraries really conveniently. Exactly
I
like you're
understand,
talking about.
except that, as you say, these libraries have multiple different forms, and that's what I'm pushing on, is we need a language basically to describe, that it isn't really a data type conversion, because it's not just data types, it's not just
yeah,
data.
but see, within the compiler, if we have sparse array in the compiler, then all we have to do is write a new data structure and
Yes.
just write a conversion to that data structure within the compiler.
I
easy as
understand
pie.
that,
And
right, but I can, that is assuming it is not just the data structure, it is also the meaning of the data structure. In other words, let's say people have, I don't know, just a two-dimensional array. It could mean two different things. Let's say it could mean multiple different things. There's going to have to be some, glue layer in which we define what those possible forms in which ultimately the series of bits that are emitted to represent a sparse array of a certain kind.
yes.
Okay, so I mean, but you think there's a tool chain there that goes through the compiler, through external. I mean, is it, in the end, when you call one of these things, it will be a library load. I mean, will you be saying library load to get this thing in, or what will you be doing?
Yeah, well, right now what we're doing is we're using this library link to do it. But yes, ultimately, once this stuff is more incorporated in the compiler, I think we'll be able to just do a library load.
And so as a practical matter, when these external optimization libraries, when you buy one of these things, do you get a blob of code that they expect you will link like that? Is that how they intended to be used?
No, when you buy all the libraries we've done so far, what they do is they give you, you can download the libraries as you want, okay, and they give you a license that unlocks the libraries basically. So the model we're using now is we're putting together packlets that'll be available by the packlet server. Okay, and you could do, say, method goes to Garobi or something, and what that'll do is it'll go to the packlet. If the first time you do that, it'll go to the packlet server, get the packlet, and then it'll, and we have an automatic thing that checks your license to make sure you have a license for it, and then it subsequently we have the libraries in the system, so it knows where to find it.
So I understand. So the way we're doing it with these companies is that they are giving us the bag of bits for their libraries.
Yep.
And then there is an authentication mechanism, and I assume that's working through our whole authentication system, is it? That
No,
it's working through their license system.
No, I know that. We've got a whole system that's been built, right? For doing, I don't know whether they're using OAuth 2 or whether they're not using something as modern as that, but we got a whole system built. If you, for example, want to use the Facebook API, right? There's a whole system where you're using our thing, but you have to log into Facebook. Then we have to get a token back from Facebook that we can then send to Facebook to use the API. Do you get what I'm saying?
But it's not like that, Stephen. This is an actual library on your system, and it's their whatever license mechanism.
I understand. I understand
so it's not
that. Okay, well, who knows? I mean, it's probably much less modern than that, I would guess.
Oh yeah.
But the fact is, the token. So, is it in the end the license is some file that sits on your system, or what is it typically?
In both of these, I know in the MOSAIC case, it's just a file that sits on your system.
Okay, all right.
So
it's a magic file that sits on your system, and that is probably tied to some license ID on your system.
Yes.
So, okay, fine. So, okay. So then there is a workflow, presumably, which tells you, go buy this thing from these guys, get this authentication piece, put it on your system, and then just use method arrow Garobi and it'll just work. Is that the idea?
Right. And if you try and use method Garobi without having the license,
it'll complain.
It'll say, please go to, and this is part of our partnership to give the right website, right?
Yeah. Right.
Yeah.
Right. I get it. It's highly sensible. Okay. So
now another thing is that many of these libraries are free for academics. So
okay, that's a whole complicated, bizarrely entwined complexity, which I'm sure we can deal with.
yeah, I think it's just great. It means that for academics, they have an incentive. You know, if you're into this and you need to use the absolutely best, there's no friction to get it.
Right.
And if it's a
But I'm sure
commercial
that
project, you will get it if it's worth it.
right.
You know what I'm saying, and it's not a problem if it's
Right.
a
But I
project where
mean,
it's worth.
but the question of how our license mechanism interfaces with what what counts as an academic organization and how we tag that
But
versus
that's
how
not
they
our
tag that.
problem. We don't touch that. They go to them and say what they are. Do you see what I'm saying? It's not.
Oh, I see.
We
I see. So you still have to get a license key from them. It's not like they're relying. I mean, it's not like what we're doing with single sign-on, for example, with universities,
no.
where, okay, I mean, that's something they could do. Do you understand what I'm saying? Because with single
Yeah,
sign-on, what's
but then we
happening?
get even deeper in bed, and it's
Well,
I don't know if
that's this is a different issue for a different group. But I mean, I'm just to paint that picture. The point is with single sign-on, we are using the directory of the university, right,
yeah.
to determine whether the person is a valid user, right?
I see.
Right? That's how it works. And
Right.
so,
And how
in a
widely
sense,
deployed is that?
well, we just started deploying it. It's being deployed very quickly. And
Okay.
lots of large universities have now already deployed it. It's only been like a month or something we've been doing that.
Great.
I mean,
No, but I
it's
think that
a
I think
complicated
that
project.
this is
Uh,
I don't think we need to tie into that. It doesn't, you don't want to couple projects that don't have to be coupled. And so I don't think that these
no,
need to
no,
be
I
coupled.
understand. Okay, we need to wrap here, but let me just answer these other questions on our live stream. Is there an AI that recommends function names? We have experimented with that. It is remarkably difficult. Seems to be still something that needs us boring humans. Let's see. When is the stochastic optimization going to be implemented? Somebody enthusiastic about it.
Most likely, I mean, we can never promise for sure. I'm sorry about that, but our intended is that they will make it for the next release following 12.2.
Ethan is saying doesn't just want sparse things, but multidimensionality and heterogeneity and so on. Yeah, all of that stuff. The plan for the way to be able to parse data is very general. And basically, if you give a seed, declaration, we should be able to deal with it. That's the idea. And I think I need to run, and this looks good, and look forward to seeing all this stuff. I wish I understood all of this better,
but you will. So all of a sudden you decided it's interesting, and then we'll have, like now for graphs, now we have massive asks every night.
Yeah, right.
I know how this goes.
Yeah, right. Well, I know it. It's yes. I just haven't. I mean, look, can you solve the problem that I've been interested in for a long time? Of Rob, I've asked you about this over the course of like 15 years. Of given does this help with the following problem? Given a graph with certain graph distances between its nodes, find a layout in three-dimensional space, for example, such that the set of Euclidean distances is as close as possible to the graph distances. In other words, that form of graph layout. You understood the setup?
Yeah.
I mean, that would be a lovely method to have for graph layout, to be able to do that. I mean, obviously that's qualitatively what graph layout does, but with some particular, L2 norm or something, being able to do that problem. Is that a convex optimization problem?
I remember you sending this about several months ago, and it's not strictly convex, but we could sort of approximate it using some of but on small scale though but so it is not convex, unfortunately.
A pity.
Yes.
I mean, that would be a lovely method to have for graph layout, even if it's on a comparatively small scale, that it tries to do that. It would be very useful for many purposes, particularly those of us interested in modeling space.
Well, something Roger has not mentioned that I think the convex will give us a basis for is so in addition to the stochastic stuff, we hope to eventually be moving into more, more general nonlinear programming. But there are, there are classes of nonlinear programming where you actually have a chance of success. And one class is a convex concave, difference of convex is what it's called. So you have a convex minus a concave plus a concave function. Mm-hmm. And those actually have some specific methods you can solve. And also using branch and bound with convex solvers underneath the hood gives you an extra thing. So it's,
I did say that, but so we have a line of global optimization problems that are non-convex, but are basically extensions in
of the methods.
Yeah.
Okay, that'll be interesting. I mean, I just have no idea how, it's like some of these things end up being generic and very useful, and some of them end up being just like.
But so yeah, I mean, like when Danzig comes into von Neumann's office and presents this new idea for a simplex method,
mm-hmm.
and Neumann says like, "Oh, that," and he'd thought of it, obviously. But then people said, they poo-pooed it and said, everybody knows that problems are nonlinear. But
right,
then
I understand. So people found a way to make interesting problems be approximated by linear, and that worked in that case. Look, let's play that another round. Mm-hmm. Let's play it to solitons. Let's play it to wavelets, right? People thought with solitons, for example, we now have these integral PDEs. Integral PDEs will be able to turn lots of problems that were horrible and nonlinear and undoable into things that can be solved using integral PDEs. That didn't work out.
Right.
Yep. So some of these work and some of them don't. In other words, given that you have a particular hammer, can the nails be developed?
I think convex has it's a pretty good momentum. It's one of the most popular classes at Stanford, just to give him an example. And so people flow in from all kinds of departments. What happens in these different areas and departments is that they are able to successfully identify classes in their domain.
No, I understand. So look, the question is, and it's hard to predict, given a particular method, how robustly usable will it be? How much is it a successful attractor for other things around it? And what I mean, for example, in recent times with our physics project stuff, these multi-way systems and their various properties turn out to be a huge attractor. Turns out a huge number of things can be thought about in terms of those. For example, the games thing that I was just doing, and it's just like by the day we're coming up with more things you can think of in that way.
Right.
And it's just I would not have predicted that particularly, but after the fact, it's kind of obvious why it's happening. And like wavelets have not had as much of as many legs as one might have thought they would, unless I'm missing something.
No, right? I agree with you.
Right. So I mean, and I don't know whether that's for want of trying or it's like or whether it's just intrinsic to the lack of robustness of the concept. Anyway, all right, great stuff. There's questions here about Nash embeddings and linear kissing number problems. Yeah, I don't know whether those are sphere packing problems convex optimization. I suspect they are.
No,
they're not.
No.
Okay, I need to learn. You see, this is the question. I mean, when you have a problem like that, it's like, can it be approximated? Is it approximable by these things or not? And do you redefine? I mean, sometimes the whole structure of the world is redefined so that something becomes a solvable problem. I mean, that's
indeed. But that's exactly. I mean, so when we introduce these integer constraints, by the time you have integer constraints, it's obviously not convex.
Right.
Nevertheless, what happens there is that we can approximate these problems using convex in such a controlled way that we can actually get the true solution.
Right.
In reasonable amounts.
No, that's interesting. And I mean, it's like taking numerical approximations and then finding the integer parts and using that to get exact results and so on.
Yes, that's effectively what's happening.
Right. Cool. All right, I got to run. Thanks, guys, and thanks to folks on the live stream.